Okay. So we'll start with the last part of the lecture yesterday, where the slides were, for whatever reason, formatted badly. And this is sort of on the idea of texture analysis. So of course, this is just a very brief introduction to make you aware of what some of the techniques that are available are and basically how they work, but not really to go into much detail. And so of course, there's computer vision classes and other courses you can take that spend a lot more time going into all the mathematics for texture and why it makes sense and how you can compute it efficiently and what the name for all the different possible metrics are. But for now, we'll just focus on sort of the very basic core ideas, and we'll have a few exercises that show you how to use them, and that if you're interested, you can explore in more detail what sort of tools are available there. But sort of the idea with textures is that you have sort of patterns in images that you're trying to quantify. So kind of initially with this class, what we were focused on is that you could take an image, you could enhance it and segment it and get out the structures you were interested in, and then do some sort of analysis on this. And where texture fits in is once you've segmented the objects or picked out your regions of interest that you want to look at, how do you analyze sort of smaller patterns or details inside of there? And that, we have a few sample textures here, where one of them is sort of a vertically striped bars. The other one is horizontally striped bars, some circles, some sort of gradients, some radiating patterns, and some diagonal stripes. So we have sort of a variety of different shapes that we can see here. And what texture analysis does is we use kind of to start the tool called the co-occurrence matrix. And so has anyone heard of co-occurrence matrix before? Oh, okay, so quite surprisingly, large number of people. And 2-point correlation function. Is that okay? 1 or 2. So yeah, so in different fields it has different names, but basically the idea of a co-occurrence matrix is that if you're looking at an image at a certain point, what's the likelihood that the points around it sort of look similar? And so if you look at sort of this kind of fairly simple example, or this equation, you go through it and you just say, so I and J here represent the different intensities, and X and Y represent different offsets. And so you take an image, you take a point on your image, and you go through and you say, is the point next to it, so at a shift of delta X and delta Y, equal to the same value as this point? And if it is, then it's 1 for I equals J, and if not, it's not. And so basically you go through all the different points in your image, and you average out as you shift over, how much is it likely to change, or what values is it likely to change to? And so this is sort of a bit messy to do. It's obviously very computationally expensive because you have to go for every point in your image, and then for every possible set of distances, and then for every possible set of intensity values. And so your search space becomes quite big that you're running across in order to calculate this. And so there's tools that do this for us. And so here we have this function from scikit-image called gray co-matrix, which simply calculates this for us. And that we can now put in sort of an image, and we can get E, I, J, D, and theta. And so basically what it shows us here is that for given I and J, so if a point is currently 0, so it's the darkest color, at a distance of 1 away in a direction of 0, so sort of directly along the x-axis, the expected value, or the sum of all the points that are also 0, is 192. And if we go up, it's also 192. And if we go up at a more steep angle, then it drops down to 184. And so we see that for our very first image, that sort of these patterns are starting to come out where it's sort of quite high along the x-axis directly, and as we start to go up, the number starts to drop down. And so this is quite tricky to visualize, but basically we can get this full representation of the co-occurrence matrix, which is 4 by 4 by 15 by 15. And so what that means for this specific image is that we have 15 different distances we go across between 1 and 6, 15 different angles we go across between 0 and 2 pi, and 4 different gray levels that we look at. And so we can look at all of these different little sub-images as little patterns that we have inside of this. And so that we see, for this image, we get sort of these, curved patterns like this because we're looking at theta and distance. For this one, they're curved, but they're shifted a little bit because the angle's rotated now by 90 degrees. For this one, they're sort of more direct linear patterns, and that we get different patterns inside of all of these co-occurrence matrices for each different test pattern we put in. And so we can do some simplification. And so what we could do is, instead of looking at all the different possibilities for I and j, we can just look at the difference in I and j. So how much is it likely to change? And so we then just average over I minus j, rather than keeping all the distinct I and j values. And this makes it now a little bit easier for us to show us sort of what's the expected value versus angle and what's the expected value versus distance. And so here we can see that versus distance, you kind of see the spacing in here. So you have this higher value and then this lower value, and this kind of shows you about the spacing across the x-axis here. And that the angles here show you that sort of at pi over 2 and 3 pi, 1.5 pi, you have these peaks which correspond to angles going this way. And similarly, if the stripes then change, this distance is now fairly flat and the angular co-occurrence sort of shifts. And so you can use this curve quite easily to measure which direction your stripes are going in. And so if you know you have stripes in some direction, you can use the angular co-occurrence to quickly visualize which direction are they likely to go in. And by finding the peaks on this curve, you can now sort of quantify that pattern. And similarly, you can see that for all of these different structures, we get slightly different curves that help us sort of distinguish the different patterns that we get. And so the idea is that you can use these tools if you're looking to distinguish certain small details in images. And so we can apply this then to sort of this brain imaging problem that we've mentioned before, where we sort of have this image, a segmentation, and an overlap. And what we can do is we can go through, so we don't really have a clear, obvious segmentation that we would do. But what we can do is something called tiling. And so basically we break up the image into a number of different blocks. Yeah, with 0 through 10, 64 through 74, so whatever we have. So each block has a unique ID, but we basically have, however many blocks we have there. But we basically have a unique ID for each block that we go through, and we just calculate that texture pattern inside of that block. And so that gives us then a value for each texture at each point in our image. And so we can now calculate texture, and usually we don't use the gray, the co-occurrence matrix directly. We use some properties of it. And so if we go back to this original reference, you can calculate this gray co-occurrence matrix, but what's actually more valuable are some of these summary metrics you can get of it. So like contrast, correlation, entropy, difference value, other values you can calculate. And so that makes it a lot easier to work with. And that you can go here, and now you show sort of the average intensity for each region in the first image. And now you have contrast, dissimilarity, homogeneity, energy, correlation, ASM. So all of these different factors are sort of new images that you've created where you calculated the average value for that texture feature inside that tile. And then what you can do is now try to correlate which of these texture features correspond most directly with the feature that you're interested in. And so you can do what's called sort of a pair plot, where you now show the values for each texture and the groups. And so red is foreground and black is background, and that you can see, our first value here is intensity. Or where's intensity? Yeah, so intensity's this one. And so they, overlap quite a bit. But if we start to look at other features, we can see that homogeneity is quite a bit lower in the brain region than it is in sort of the normal part of the image. And by going through this, we can help come up with features that are more useful for figuring out which might be part of the brain and which ones are not. And so in the exercises, you then have a couple tasks where you do this, and then you actually try to build something so that you can use some of these texture features to distinguish between two different types of, I think, the mitochondria problem again. And so using textures and patterns, you can get more information and do a better job of sort of separating these two. Is there any questions on that? Before we move on to the complex objects. Okay, so you can always ask during the break. So for sort of the complex objects and distributions, again, a lot of the same references we've mentioned before. A bit more of an emphasis on the image processing handbook here. They talk about a lot of these techniques in quite a bit more detail than we do. And then there's sort of a number of papers and sites that you can go to if you're interested in reading more details about some of these approaches, because again, we just go into the sort of very basics of them. And yeah, so as I started to mention before, kind of we've covered these different techniques before. We just did the simple shape analysis and texture analysis, and even sort of got into some sort of more complicated shapes and thickness maps. And so we sort of introduced that idea at the beginning of the last lecture. And now we're looking to sort of go beyond that. And so the first part is sort of the motivation. So what sort of problems are we trying to solve with this? Then how do kind of skeletons fit into this? So tortuosity and other metrics we can calculate from sort of a skeleton once we've done it. And then watershed segmentation and how we can deal with sort of objects that are connected very closely together. Then we'll talk sort of a little bit about local environment and global environment. And so we'll have some ideas about sort of neighbors, Voronoi tessellation, distribution tensor, and then this idea of global environment with alignment, self-avoidance, two-point correlation function, linking again back to that texture idea. So the metrics that we'll sort of talk about in this lecture that are a little bit new here are kind of divided into two categories. We have this idea of sort of local metrics and sort of more global metrics. And that we can kind of look at them as sort of, point operations or voxel operations. And so point operations are obviously things that we do once we've done a segmentation and we have something like the center of volume for our object. And so there we can calculate nearest neighbor, we can do triangulation, we can do center of volume based Voronoi tessellation, we can do alignment, a number of metrics like that. And for voxel operations, we then have operating directly on the voxels without a existing segmentation or definition of what an object is. you can do Voronoi tessellation, neighbor counting, and then this 2-point correlation function, which is sort of the texture stuff we mentioned. So for the learning objectives, the first thing is kind of how do we extract topology of a structure. So when we segment complicated structures, we might do distance maps and thickness maps and get a nice visualization of them, and perhaps even quantify some simple like thickness measurements for them. But it doesn't give us a good idea of what the topology of the structure actually looks like. The second part is kind of how do we identify separate objects when they're connected. And so if we have a bunch of things that are connected together, how can we start to separate them? And so in the example of sort of the foam that we had before, where you have all of the bubbles that are touching and connected to each other, but you still would like to identify sort of where individual bubbles are. And then sort of how can we compare shape of complex objects when they grow, and sort of what metrics can we introduce for that? So what we started off with before was this idea of the sort of distance map of the foreground and the background, and we used kind of fairly basic images for doing that. And so we have this image here where we have the segmented sort of holes in the bone, and we can do a distance map of the foreground to see something about the size of the objects in the image. And we can do a distance map of the background to see something about the spacing between the objects in the image. For sort of distribution, what we saw with these images is, we get some idea for distance map of the foreground and distance map of the background. So we see some thickness ideas here and some spacing ideas there. And if we wanted to kind of investigate which of these, we think the cells that are more closely dense packed together are probably alive, and the cells that are further apart are probably dead, then we could use something like the distance map to try to quantify that. And so right now the distance map doesn't make that really easy, because you kind of have to go and find regions that were high or low, and if a region was low, it doesn't necessarily mean it's close to a lot of cells, it could just mean it's close to one cell, and so it's probably not the easiest tool for quantifying that. So for getting a quick visualization, it's very helpful, and things that are far away from every cell are quite easy, but getting an idea of the density cells isn't very easy in that. And so, if we want to know which cells are alive or more densely packed, we can examine the raw positions. We can look at sort of the visual inspection of the sample, but again, that's not quantitative, so we can look at the sample and try to go through it, but we don't really see, how do we compare two samples together. If you looked at all the raw positions of the cells, you might be able to do something with this by looking at averages and standard deviations, and maybe if it were too far away from the average, it was more likely to be sort of less dense. We can make boxes and count the cells inside each box. But, if we make a bigger box, we're going to find more cells. If we make a smaller box, then we're going to find less cells. And how do we kind of normalize that well? And then how do we compare sort of two regions in the same sample or even between two samples and do this kind of reliably? And so that's where a lot of the distribution stuff in the second part of the lecture will come in. And so what we need is sort of a way for counting cells in a region and estimating density well without creating arbitrary boxes. We need a way of finding out how many cells are near a given cell, sort of its nearest neighbors. And so this isn't like k-nearest neighbors or with the classification or regression problems we have. This is just counting the number of physical cells that are nearby. We could probably use a similar technique, but it's not trying to classify or do anything. It's simply trying to count the number of neighbors that you have. We want to quantify sort of how far cells are apart and compare their different regions within a sample, and a way of sort of quantifying and comparing orientations. And of course, what would be nice is if we had tools that really expanded beyond just single cells and were able to handle lots of different structures, lots of different phases, and help us analyze that. The next part of this is this idea of sort of destructive measurements. And so a lot of times we can't image samples without sort of destroying them. And so if we're trying to sort of track something that changes over time, it's often very difficult to do that because once we've measured it, we've sort of destroyed it, or at very least sort of influenced what we were trying to measure. And so if you're trying to look at, how embryos grow or how a bone heals, and you want to look at really high resolution images of the bone, then by sort of definition, you're going to have to take out a sample, destroy it, and measure it very well. And so if you want to now compare how did it look after month 1 versus how did it look after month 3, you've destroyed the tissue that you measured at month 1. And so you can't compare the tissue you had at month 1 to the tissue at month 3 anymore. And so you need to have techniques so that you can sort of match these different problems up. And so what this sort of comes into is that we want to have the ability to compare samples that came from different specimens without being able to sort of register everything together. And so obviously if you have an image before and after of the same person, you can sort of find the same points in the image, track them, and see how that structure changed. But if you have two different people and you want to see, what effect did smoking for 20 years have, you can't look at that person as if you don't have the counterfactual of what did they look like if they hadn't smoked. You simply have the two different images, and you have to find ways of comparing them without actually having both pieces of information. And so that's where a lot of these other techniques that we'll again talk in the second part of the lecture about sort of come into play. And so now for sort of the first thing we'll talk about is sort of a concrete problem with skeletonization and networks. And so for a lot of structures like cellular materials, trabecular bone, we want a more detailed analysis than just thickness. And so the thickness we talked about in the last lecture, which goes up here, gives us a very nice picture. It's also very useful because we can do quantitative analysis on it, so we can measure sort of distances and see how large objects are. But for a lot of the questions we're interested in answering in sort of material science, it's actually not that useful because we want to know how well things are connected together and what flow rates would happen through the structure. And so we actually want sort of beyond just the thickness. The thickness is obviously very helpful, but if we can get some information on how things are connected together, which parts are connected together, and then combine that with the thickness, that makes everything much more useful for us. Furthermore, when we start looking at sort of more network analysis, we then become much more interested in quantifying, things like tortuosity, so how sort of direct are the paths that you can take through a sample, how much branching happens, and so with complex structures like lungs, measuring how much branching is occurring can let you know how well the lung is working or how far along in development the lung is. And obviously for lots of other examples, there are plenty of use cases where knowing the network and quantifying it is very useful. And so the easiest, sort of most applicable use case for most of you is this kind of aerial image. And so companies, NASA earlier, and now lots of private companies are doing sort of satellite imaging of the world. So they have satellites up. One of them called Planet Labs, or just Planet, I think has satellites up where they try to take a picture of the world every day. And so that's their goal. And so they fly satellites around and they take thousands and thousands of pictures in high resolution to see sort of what's changing, what's going on. And kind of one of the simplest tasks you would have with this is if you get a picture of a country that you don't have any maps for, or even if you did have some maps for it, you want to be able to kind of figure out, where are the roads and how are the roads connected in this. If you wanted to offer like a Google Maps-like service, you'd have to know first, what are the roads, how are they connected, which ones can you take, and you'd need it to actually be fairly reliable because if you have one disconnect in your graph, then your ability to give someone directions is completely gone. And if you connect things that aren't supposed to be connected, then again, you give them directions that they're not able to follow. And so the task we'll have is this sort of idea of how can we go from an aerial image to a network of the road. And what's quite nice with this is because EPFL has a public data set, we can take their manually labeled data, where they had students go through and manually click where all the roads are, as a sort of basis for evaluating if our approach is working well or not. And to kind of show this example, we'll focus on just a little small region of the image that makes it a little bit easier to do. And so the first task that we have with this is to kind of even figure out what things could possibly be road. And how would you go about doing that? Or any ideas on what your first step would be? What? Yeah? And how would you segment? Yep.
And then there will be smaller feature that will interfere with this bigger road, so that we have to also erode them.
Yeah. 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 So the first thing is segmenting. And what we have is that we don't have a grayscale image here. We have a color image. And so we can either first convert it to grayscale and then segment the grayscale, or we can keep the color because actually the color is quite helpful. That we know roads aren't green, at least not in this example. Roads are also not blue. And so we can eliminate a number of the other objects by using color quite easily. And but it's not sort of complete because the road color and the roof color of these houses is very similar. And so if we just did it by color, we'd still get sort of a lot of issues. And so we can see that we can convert the image into something called sort of an HSV representation, which is sort of hue saturation value that tries to get the color information separated from how sort of rich the color is and how bright the color is. And so I think this is the right image for it. This one. Yeah. And so hue shows us sort of the angle around the axis. Saturation shows sort of how close, how far from the center we are. And value sort of shows what we would call kind of brightness. And when you take normal images with sort of your camera, they come out as sort of RGB images where you have red, green, and blue. But that's not always very easy for comparing. And so what hue saturation value lets us do is kind of separate, a blue that's slightly well lit is going to be sort of just down on the value axis rather than down on the red and green and blue axis. And so it gives us a better way for separating the colors. And so when you have color images, this is often a much more useful representation because then you can just say if you want green colors, then you keep all the hue values between sort of, 100 degrees and 120 degrees, and all the saturation sort of above 0.5 and all the values above a certain brightness. And so it lets you kind of separate those things more easily. And so this is quite easy to do. We have tools that do this for us in Scikit-Image or OpenCV or KNIME. And so what we can do is we can take sort of the image and apply this HSV and then just keep the value image. We could also change this to just keep the hue image or just keep the saturation image and see how that would sort of change the results. There we are. And so here we have the value image. If we went to hue, takes a few seconds, but that we would then see we could choose sort of a different channel to use the information from. And for this one, value made the most sense, but for other cases, hue might make sense as well. Okay. I guess we can come. Oh no, there it is. Loaded the wrong image. Okay, so there we are. So if you take the hue instead, then you get sort of an image where you see the kind of different colors in the image, or sort of the different points on the hue spectrum, and that would be very useful if we had a sort of brightly colored image. But for our case right now, it's quite a bit more difficult to see because the hue, in particular, doesn't really have much of a meaning if the value is really low. So if you go back to this image here, if value is 0, then all the different colors in black have the same hue. Similarly, if saturation is 0, then everything's white, and it really doesn't matter what that angle around the axis is. And so points that get very close to here or very close to there end up having kind of meaningless values of hue, which is why we see kind of all of these weird structures that aren't actually reflected in the image, because in points that are sort of really bright or really dark, that hue doesn't have any meaning anymore. We could also just look at sort of saturation, where we see the roads fairly well, but also the houses are pretty clearly marked on there too. And so we could choose to use saturation instead of using value. It doesn't make too much of a difference, but for this example, we'll use value. But it's always important to kind of look through these images and see kind of what the different images look like, which one keeps the most structure, which ones keep the information that you're interested in, and make it easier for you to kind of segment. And so we can take our first segmentation and see that that looks pretty bad. So we certainly have most of the roads in it. Importantly, the roads that we have in it are all connected, so we're not missing any connections. And so now, as you mentioned, we can go to kind of the next part of eroding and labeling. And so we can kind of get rid of the smaller features by using eroding and opening operations. And then we can do labeling. And so once we've done a little bit of that, we can now group everything together into different objects. And then if we sort everything by how large the object is, we now get sort of these, 35, 36 different groups. And we can see that there's sort of the one main road object and then all of these little smaller objects. Yeah.
Hopefully not the rest of the question. So this saturation value works with only with the RGB image. So we always have to transform in RGB our image then.
If you have a grayscale image, it probably doesn't make sense to convert it to RGB and then convert it back to HSV. So it only works if you have real colors in it in the first place. So if you take a grayscale image and convert it to RGB and then convert it to HSV, then you won't get any new information out of it. So HSV is just for taking the different colors that you have and projecting them well. And so if you had a grayscale image, basically everything you would have would be no hue at all, and it would be along this line in the middle. And so you won't really get any new or better information from it, but with dealing with RGB images, it's quite helpful, because dealing with sort of red by itself isn't always, that if you don't happen to be interested in the colors red, green, and blue, and you're interested in yellow or teal or red, orange, then using the HSV representation can make it a lot more intuitive to work with.
Because when you have RGB image, you divide by the three colors. You can always use one of the colors that satisfy your Western static from there. Basically.
For what?
If you go in red or blue, or you divide the picture into three
Yeah.
colors basically, and if you want to track something that has more color in red,
Yeah.
it will appear more in that picture.
Right.
Can
So you can.
approach, or it could be wrong.
Yeah, I mean, so the problem with saying that, like, I'll just use the red channel and that will show me what things are red is if you have a grayscale image and you have a white spot,
Yeah.
then the value for white is really high in red and really high in green and really high in blue. And so when you use the HSV approach, you can get an idea of what color is it separately from how bright is it, separately from how saturated is it. And so it gives you sort of an easier representation for that. Yeah. But it's not magic. It doesn't make your problem that much easier. It's just for a lot of things a lot easier than using red, green, and blue directly. So we can see here that we have sort of these images now that we've been able to label. And this is where we can then kind of do a fairly simple hack where we say we just keep the largest object. And so we throw away all the objects except for the main one, or except the objects that are larger than a certain size, rather than trying to perform erosion or dilation until we get rid of all of these. Because the problem with that is, to get rid of something like this big house could take a lot of erosion and dilation operations and would very likely then break the connection to this street. And so it's easier to get rid of these objects just by deleting them than it is by kind of trying to erode a really large object away. And so now what sort of skeletonization does is it starts with the distance map that we covered before, and we take sort of the distance transform of the structure. So we have this sort of black and white image, and that we take the distance from the border to it. So we take this largest component and then calculate the distance to the edge from every point inside this component. And so now what this gives us is sort of each point, the number of pixels it is away from the surface. And so this is clearly downscaled. So we leave out a lot of the pixels so that we can see what the actual values are. And then what we can do is do something called sort of ridge detection. And so when we look at this distance map, we can see that there's kind of like a ridge that goes along the backbone of this object. And that kind of intuitively is the skeleton. And so if you think of this as kind of a topological map or something along those lines, that you can kind of look at this object and see this, if this were, mountains, this would be a kind of chain of mountains along the top, and that's kind of what we want to segment. And we don't want to keep all the other points, we just want to keep that ridge. And so what we can use are some of the filters we talked about in the third lecture, where we can kind of focus on sort of an edge detection inside this and look for that kind of local minimum. And so what we can do is we can look at kind of where that's flat and minimum distance away from the surface. So we sort of have two requirements that we apply, where we can now say, this is the Laplacian for the distance. We can see that that ridge now becomes very clear inside our image. And we have some large values near the edges, but we can ignore those because they're too close to the surface. But that the very first approach we take gets us much closer to kind of that topology that we're interested in, rather than having all the pixels from the road. And so we can then take a ridge out of this by simply keeping the values that are above a certain intensity. And so it's not quite the road we were looking for yet, but we now have at least sort of a single line of things that's connecting all the points in the road together, rather than having all the pixels that we wanted to look at in the road. We can now use techniques called sort of morphological thinning, where we can apply it to the structure kind of before we perform the segmentation. And so what morphological thinning does that's quite useful is it's thinning that preserves the morphology. And so it just tries to delete pixels that don't end up changing the skeleton too much. And then we can perform an opening operation to get rid of all of the things that are sort of left over still, and then perform that skeleton operation again, so that ridge detection again. And so that we can see by doing that, we go from kind of a very messy skeleton with all kinds of extra loops to a much cleaner one. And so it's still not perfect, but it's getting a lot closer to something that actually looks like kind of a road map. And so it's still quite overgrown, but we can probably start to improve it on our own at this point. And so here we can look at sort of junction count, and that's going through all the pixels in the skeleton and counting how many neighbors each pixel has. And so if you go through each point and say if it has, one neighbor, then it's a terminus, so it's over here. If it has sort of two neighbors, then it's a segment. That means it's sort of part of a line. And if it has more than two neighbors, then it's a junction. And so all these white points now represent sort of junctions. And so that we can zoom into one little part of the image. And here, well, if you count itself, then those numbers shift up by 1. But that basically this point sees 2 points, so it sees itself, and then it sees the point next to it. This one sees 3 points, so it sees that point itself and the point on the other side. And this point sees 4, so it sees this one, it sees itself, this one, this one, this one. And so it's sort of a little box operation, convolution that you perform on your image, which basically shows you how many voxels are part of your skeleton inside that point. And so now we have something that's kind of a much better topological representation of what we're trying to look at. So I think we'll take a break quickly here, as this is printing time, and then are there any questions on that? Yeah.
How do we remove the small segments like are probably the garbage space outside where
That's the next slides, yeah.
because this is what it's like. We might have to do some hard coded threshold, and in that case, in the beginning, we also have a predefined value for as the other colleague said about the color of the road.
Yeah.
We can give that as an input, or
Yeah.
Okay, we don't have to detect that from the image.
No. I mean, there's certain things you want to detect, and there's certain things that you want to find out for yourself. And so for the segments, there's no roads that are less than, 20 meters long or something like that, or that it's probably not a road, or that if it's too narrow, it's probably a sidewalk. And those are things that you don't really want to have your system learn. You want to give it as information because that's very useful for what you're trying to do.
But then the criteria to define those values
Are hard-coded.
Okay.
Yeah. Because, when you look at the image, it's not clear. I mean, there are sidewalks as well. Sidewalks are probably interesting for some problems, and you really have to then tell it this is not what you're trying to find. Yeah. Okay. So we'll have a short break, and then